feel like we're missing a few people, but that's okay. We'll get started. So today I want to go over some related rate stuff. And just as a reminder, the related rate assignment right now, I haven't changed it yet, but it will be due on Monday. And then we'll have the exam either Wednesday or Friday of next week, depending on when you take your exam. Today, for the related rates, I don't really want to do a bunch of the problems. And the reason for that is, I'll help you get started if you kind of need a push in the right direction. You're kind of like, how do I even start something like this? I'd love to help you with that. But I ultimately want you to do it and to get better at these. There's no real good way to get better at related rates problems than just doing them. So it's not actually that helpful to you if I do 6 of them. It will just make it so that that's 6 less practice that you get. So you'll have plenty of time to work on these over the weekend. So I want to give you the time to do that. But I would, if there was one that you were looking at and you were kind of like, I didn't even know where to get started, I would be happy to give you a push in the right direction. So yes, sir.
28.
28.
I need a push.
Okay.
A large push.
All right. 28. Oh, the baseball team. Okay. So runners at first and second base. Okay. Okay. The moment the ball is hit, the runner at first base runs to second base, and the runner at second runs to third at 20 feet per second. How fast is the distance between the runners changing 1 second after the ball is hit? Okay. Okay. So it's 90 feet between bases. All right. So let's set this up a little bit. We've got our baseball diamond, right? We got our So here's our baseball diamond, and we've got a guy on first that when the ball is hit, he's going to start running to second base, right? So we've got somebody on second base that when the ball's hit, he's going to start running to third base. And what's going to happen is there's a distance between those two guys. Okay, now, obviously when time equals 0, like the instant the ball is hit, we actually know the distance between those two guys, right? What is it? 90. Yeah, so it's 90 as soon as the ball is hit. Was the time they were interested in 1 second later? Let's see. Yeah, 1 second after the ball is hit. So this guy's running at a certain rate. This guy's running at a certain rate. Was this one 18 feet per second?
The runner at first base runs to second base at 18 feet per second.
Okay, and then the other one was 20?
Yes, correct.
20 feet per second. Okay, so after a second, this guy moves up, right? Also, after a second, this guy moves up, and we get that distance. Let's call that D. All right, so that D will just be the distance between the two runners at any given time. All right, so what that does for us is we need to somehow get involved some variables. There are no variables involved right now. And so what I could do several different things and they're all fine. So I could call this distance right here X. I could call this distance between this point and this point X. One of those needs to be X. It doesn't really matter which one. You just have to be careful with what you're doing. So I'm just gonna, for now, let's call this distance X right here, which means what is the distance between here and here? What's that?
90 minus X.
Yeah, 90 minus X. Right? Because the total distance is 90. If I take X out, this must be right here. 90 minus X is from here to here. Similarly, I could call this distance, let's say Y. And then this distance right here would be 90 minus y. Okay, so what I want to do is I want to relate all of these things, the x, the y, and the d. But I see that I have a right triangle right here. Okay, so this right triangle gives me that 90 minus x squared plus y squared is equal to d squared. Correct? Okay, so this is a very good start to this problem. Because now what I could do is I could take the derivative of both sides implicitly, and then I could start plugging in what I know. What is it that I'm trying to figure out? Yeah, so they're trying to say how fast is the distance between the runners changing? And that's one of the key words in these problems is the word changing means rate of change, means derivative. And so we're trying to find the derivative of this thing d, right? Maybe dt is kind of terrible. Maybe I should have called it something other than d. Maybe I'll call it, I don't know, z. Make z the distance between the runners. And then we could say that what we're trying to find is dz dt. But now I have a relationship, and to find dz dt, once I take this derivative, well, I could take it really quick if I wanted to. This is 2 times 90 minus x times the derivative of what's inside. But the derivative of what's inside is minus dx dt. Okay, the derivative of y squared is 2y dy dt. And the derivative of z squared is 2z dz dt. And what I want to find is dz dt, correct? So what I'm going to have to know in order to find dz dt is I need to know what's x at this specific time I'm interested in. So in 1 second, how long is this distance in 1 second? 18, because he's run 1 second, correct? Then I would need to know what is dx dt. Well, dx dt is how fast is x changing? Well, we know that that's a change, a rate of change. So we're asking, how is x getting bigger? Is x getting smaller? And you need to be careful on this because sometimes dx dt could be positive, sometimes it could be negative. In this case, is x, as this guy runs, is the distance x getting bigger or smaller? Bigger. And so it's a positive value. So this dx dt is just going to be my 18.
So what does that make x in your 90 minus x?
Good. What is x? Oh, you mean in 1 second?
Well, so dx dt is 18.
Yes.
So we got negative 18. So we got 290 minus x times negative 18.
Yes.
Right. What is that x then? 90 minus x.
It also is 18, but not for the same reason.
Okay.
It's because he's run for 1
The
second.
position is 18.
His position is 18
Gotcha.
after 1 second because the change is 18. Does that make sense?
Yeah.
Yeah. So x is 18, dx dt is 18. What's y in 1 second? So that's this distance. So how far has he run in 1 second? 20, right? What's dy dt? Also 20 for a different reason though, because that's the rate of change. And then finally, what's z? How would you figure out what z is in 1 second?
Divided by 2. Now that you hold number 2 divided by 7 by 2z. No, you're right.
Well, this is a right triangle, right? And you know some sides of it. You know that this side is 20 after 1 second. What's this side?
That's 72.
Yeah, 72. And so you should be able to figure out if you have 20 squared plus 72 squared, that should equal z squared, right? So you can solve for z, plug it in for z, and then you just have all numbers and you can solve for dz dt. Okay, so I'll leave, that's most of the problem actually that I just did, but it gives you a good feel for how you would do this sort of thing. Yeah.
So if you have made, instead of 90 minus x, so that second triangle will be x, then dx over dt would be negative because x is decreasing.
That's right. So I made it x and y here just so it would keep the dx dt and the dy dt as positive values. But like I said, I could have made this distance x and this 90 minus x, and then this would be x squared plus y squared equals z squared, which seems really wonderful, but you just have to be a little bit careful that you say, okay, but that means that dx dt is actually a negative value. Yeah. Say that again. Yeah, I did, but that's because of what I was taking the derivative of here. But dx, okay, what I'm saying is when I plug in for dx dt here, it's positive. If I would have started with this thing being, if I would have, instead of making this 90 minus x, if I would have made this distance x, then this would have been an x squared, and this would have been 2x dx dt, but dx dt itself would be a negative number. Are you catching what I'm saying? So you can set this up differently, and it all works, as long as you're keeping track of really, okay, is this thing, is x growing, or if x was here, x is shrinking. So that means it must be negative. The way I set it up, x is here and it's growing, so dx dt is positive. Make sense? Okay. Any others? Yeah. 36, sure. Okay, so we're draining a tank. Okay. So 36, we have a cone. Okay, so an inverted conical water tank with a height of 12 feet. That's 12 feet. And radius 6 feet. So from here to 6 feet. Is drained through a hole in the vertex at a rate of 2 feet cubed per second. Okay. What is the rate of change of the water depth when the water depth is 30 feet? Okay. Yeah. So the thing I really need to know here is I need to know, I guess I can put in some little other variables here before I start, is first I've got some sort of a height of the water. Okay, and I'll call that little h. And I have some sort of radius of the water. I'll call that little r. Okay, just to get some variables involved. Then I need to know what is the formula for the volume of a cone. Anybody look that one up? 1/3 pi r squared h. I think so. 1/3 pi r squared h. Okay, so this is kind of my formula that gets everything involved. It gets the volume of that cone, which, by the way, if it's draining, what is changing? Yes, the height and the radius and the volume. That's right. And what we know something about is we know something about how fast is the volume changing, right? It says that it's draining out at what is it? Cubic feet per second or something?
Yeah.
What is it?
Oh, sorry, yeah, two cubic feet per second.
Yeah, 2 cubic feet per second. Okay, so so what I need to do is I need to sort of relate all these things. By the way, something's not so great here is that I don't really know anything. What do I want to find? So reading the problem, they say, you want to find what? What is the rate of change of the water depth?
So you want to find DHDT?
DHDT, the rate of change of the depth, right? You don't want to find the depth. You want to find the rate of change of the depth. So the depth in this case is represented by H. And so we want to find DHDT. Okay, if I took the derivative as is, to find DHDT, I'd need to know dVdt, or the change in volume over time. Do I know that? I think I do. It tells me that the change, they say that it's being drained at a rate of 2 cubic feet per second. Being drained, what's changing? The volume. So that 2 is a change in volume. So that's my dVdt. I'd also need to know what's drdt. Do I know that? That it doesn't tell me anything about that in the book. And so what I'd like to do is I'd say, okay, I don't know what drdt is, so can I get rid of r? And the answer is you can, using similar triangles on this cone. So look at this. I've got this triangle, which is a right triangle. And I've also got this triangle, which is a right triangle. Those are similar triangles. So that means that I could say something like h over 6 should be the same. Wait, not h over 6. That's a lie. I meant to say 12, like the height of the big one over 6 should be the same as the height of the little one over r. So this is, and then I should be able to, so that's just using similar triangles, right? That 12 over 6 is h over r. I could solve for r. If I did solve for r, I'd get that 12r is 6h. And then r is equal to, let's see, 1/2 of h.
So you're given a height, or a height where they want you to find DHDT.
Yes.
Can you use that little h in that equation? So r is equal to 1/2 3?
No.
No. Okay.
And let me tell you why. So this is saying this is the volume at any time.
Okay.
So I'm using this as the volume of the water, not the volume of the tank. We could easily calculate the volume of the tank. It's just a fixed cone. The thing that's changing is the unfixed little cone of water, right? And so you can't, this is actually super important. And that is, you don't plug in values for variables that aren't rates of change until after taking a derivative. So if you haven't taken a derivative, but you plugged something in for like r, or you're like, oh, wait, the height where I care in this problem, what is it? They say when the depth is 3 feet. So you might be tempted to say, oh, wait, I know that h is 3. So let's just plug that in. It's like, well, that's not right. H isn't 3, h is h. But at different times, we could figure out what that height is. And they're saying, when h is 3, what are the other things? Well, you can't plug that in until you've taken a derivative. And so in this case, we know that r is equal to 1/2 h. So what I'm going to do is I'm going to take that r and plug it in for r right here. The reason I want to do that is I don't want any more r's in the equation because I don't know what drdt is. So I plug it in and I get that v is 1/3 pi R, but R is 1/2 h squared times h.
So you take the derivative. Now that you have gotten rid of all your r's, you take the derivative.
That's right. So now, and maybe I want to write this one more time just to clean it up a little bit. So let's see, 1/2 squared is a 4th times a 3rd is a 12th. So I have 1/12 pi. This is h squared times h. So this is h cubed. And that's a very nice formula. So this is the guy that I'm going to want to take the derivative of. And it doesn't have any r's in it, so I don't need to know what dr dt is. Okay, so now I could take the derivative of both sides, and I get dv dt is equal to, I bring down the 3, and I get 3 over 12, or 1/4, pi h squared times dh dt. And we're almost done here. Now I just need to find, well, what is, so to find dh dt, which is what I'm trying to find, I need to know dv dt, and I need to know h. Do I know both of them?
Yes.
Yeah, they're both given to me in the problem. So, but what is dv dt a positive number, or is it a negative number?
It's positive, but because you're draining would be negative.
That's right. So I have to say, as time moves, does the volume get smaller or does the volume get bigger? And in this case, I'm draining the tank. So the volume's getting smaller. So dv dt should be a negative number. So even though it's given as it's draining at 2, but it's like, yeah, but that means it's going down. So I need to make that negative. So this dv dt would be a -2. And this is 1/4 pi. They give us h, right? They say at height, is it 3?
Yeah.
Yeah, this is a 3 squared dh dt. And now I can just divide both sides by this value and get my dh dt. So let me just do it since we're right here. dh dt is equal to, let's see. So we got this -2 over, I guess we'll divide by, this is 9/4, 9/4, and the pi is on top. So 9 pi over 4, or if you like, that would be -8 over 9 pi. What's the, if you wanted to put units on this, which is always a good habit of doing when you have problems like this, what would the units be? Well, I use a trick to figure out what my units would be, and I just ask, if I'm finding the change in the height over the change in time, then I say, how is the height measured and how is the time measured in this problem? And in this problem, how is height measured? Yeah. So yes, that would be the answer, because height is measured in this problem in feet, correct? No, because h is only measured in feet. Now volume is measured in feet cubed, right? So if I were finding a dv dt, then I might be saying feet cubed per second. But if I ask myself, how is height measured? Like if you're measuring a height, you would never say this height is 10 feet cubed, right? You would say this height is 10 feet, right? If you're measuring a height, it's just in feet. So it's feet, and then time is measured in this problem in seconds, correct? So this would just be feet per second. And that works every time, actually. You can just ask yourself, how are these two things measured in this problem to figure out what the unit should be at the end.
So on a test or homework, I'm trying to plug this in my calculator. I'm not getting nice numbers, but
Right.
I keep on random numbers. Leaving it as -8/9 pi is acceptable.
Yes. Another question I have for you is, does this answer even make sense? And what I'm saying is that the change in height over time is a negative number. So I would always go back and say, in this problem, as this tank drains, is the height going down or is the height going up? The height should be going down. So you would expect that the change in H over time is negative. If it were positive, then I'd be like, uh-oh, that's not good. Would you agree? Because I'm saying that the height is going up over time while it's draining. Then you did something wrong. Does that make sense? So that's always a good thing to go back and ask yourself. Once you got the answer and you said that the change in height over time is negative, you should say, oh, that means the height should be shrinking over time. And in this case, it is. So that makes sense.
So then on the first problem,
Yes.
Right? If the answer we got was negative, that would mean they're getting closer together or farther apart.
Okay, so you were trying to find dz/dt.
How quickly they're.
Yeah, so you got a negative number?
I got a negative number.
Okay, so if you got a negative number, that means that the distance between them is actually getting smaller at that moment.
Yeah.
But it could be that later on in the triangle, it starts to grow again.
Yeah.
So at that moment, they're getting closer, and that kind of makes sense because they're kind of like getting closer to that isosceles triangle, which might be it would be interesting, that might be their closest spot, right? Well, they're not actually going to hit it because they're not running the same rate, but they're going to get to their closest point somewhere in there. And that would be an interesting problem that we'll actually do later in this class, is like, well, what would be the closest they ever are, right? That's an interesting question. And that's what we call, and this is maybe one of the most important parts of calculus, is it's called optimization. It's kind of like, at what point in their run would they be the closest together? That's an interesting question. It's not the one we're answering right now, but it kind of brings it up. But right now you're seeing that they're actually getting closer together as they run. And you know that eventually they'll just be 90 again. So they started and they were 90, and as they run, they're getting closer. So if you actually calculated Z right here, which you did for this problem, I'm guessing that it's less than 90, right? So they're getting closer together at some point until they hit a kind of critical point, and then they start getting further from each other again. So yes, they're getting closer together, long story short.
And then on the process, just kind of unrelated rates problems. Yes. I'm seeing a pattern of starting with the shapes kind of integral, not integral in the sense of the squiggly line, but most integral formula, right? So you're starting with Pythagorean theorem, you're starting with the volume of the cone. Is that something that's always going to be true, that you're starting with that kind of formula? And
even the word related rates, the first thing that you need to do is find a way to relate all the variables. So it's like, you've got a picture. Usually you draw a picture. Like I drew a picture here, I drew a picture here, and I start writing in like some variables, right? So you've got a bunch of variables, or here you've got, like, this is kind of a tricky one in some sense because even the variables I wrote, V's not involved. But I know I need to get the volume involved. So this one, actually, it's pretty easy to know what's that related formula. Something over here, you kind of maybe have to look at it a little while and say, oh, actually, we're dealing with a right triangle. And so that right triangle will get X's and Y's and Z's all involved in the same formula. So that's what you're trying to do first, is you're trying to figure out what's the formula that gets all of the necessary variables involved at the same time. Once you've found that, then you can kind of start saying, okay, I need to take a derivative of that formula that relates everything. But can I? And is it going to be helpful to? Like over here, I knew everything I needed to know. So I can just go ahead and take the derivative. Over here, when I look at this one, I am saying to myself, okay, I'm trying to find dH/dt, which means I'm going to need to know dV/dt and dR/dt. I know dV/dt, I don't know dR/dt, so I have a little bit more work to do on my formula before I take the derivative. I remember I have a story. I was like in graduate school, and I was coming home for Christmas, and I picked up my brother from college, and he was like a freshman in college, and he had just taken an exam in Calculus 1 over this exact section. And I remember asking him, oh, what was the problem about? And he told me, and I actually think it was kind of like something like this baseball problem. And I was like, oh, yeah. And I said, so what did you get for the derivative? And he was like, I don't think I took a derivative. And I was like, you got it wrong. Sorry. So one thing that you need to kind of keep in mind on these problems is like, you don't start doing the real work on these problems until you take the derivative. Okay, if you start plugging things in before you take the derivative, chances are you're wrong. Not chances are, you're wrong. Okay, so don't start plugging things in until after taking a derivative of whatever the important formula is for that problem. So that's kind of the hardest part in some sense, is like, well, what's the important formula? And there's no like, well, it's obvious, it's this. You have to actually think about it. So it could be like relating things with a tangent formula. It could be, a right triangle. It could be some sort of a shape that you're using. There's all sorts of things that it could be. You just have to figure out what is it that relates all the relevant variables. Okay? Other questions? Yeah.
So this is just a general question, kind of goes off one of the examples you gave, but
Yeah.
like in the final example you gave with the boat being pulled,
Yes.
we got an x value, and when the dx over dt value was greater than the hypotenuse of the triangle rate that was given. But isn't that, like, if you look at physics and vectors, won't the hypotenuse always be greater than?
Okay, say that one more time. I'm sorry.
So basically, I guess the end answer, I just calculated it out because it was in the next square root thing, but like, it was the boat was being pulled at the rope was being pulled at 3 feet per second. The dx over dt was 3.2 feet per second.
Yes.
How does that work with physics, I guess?
Yeah. So you're saying that the hypotenuse was being pulled at a rate, but the rate of into the dock was actually faster than the rate. Yeah. Okay. So what's interesting about that is it depends on where you are in the pull.
Okay.
So what happens is, and you're kind of saying, well, how could it possibly be going faster? Yes, that's right. So you're pulling a rope in at a constant rate, right? Now, if the boat is very, very far out, then the rate at which you pull into the dock and the rate at which the boat is sliding in horizontally towards the dock is going to be pretty similar. But as you get closer and closer to the dock, it actually will kind of speed up, right? And it will, like, at the very last moment, if you just kept pulling, that would be a bad idea, right? Because you would smash the boat into the dock, so to speak. So it does actually speed up. It's the same thing with like the ladder problems. I think I did a ladder problem in one of the example problems. If you haven't watched it yet, I would watch it. But as a ladder slides down a wall, if I'm just kind of walking the ladder away from the wall, you would think that, like, well, there should never be a point where it's going down faster than what I'm pulling it out. But it's like, no, it actually does. And at the end, it slams down, right? If I was taking like a ladder and I was just slowly walking it away from the wall, at the very end, it would just go boom, right? And it's like, that's going pretty fast right at the end. So the rate of change, I think what is confusing is, like, for the actual hypotenuse and length, certainly the hypotenuse is always going to be bigger, but is the rate of change of the hypotenuse always going to be bigger than the rate of change of like a leg? Not necessarily. Is that helpful?
Yeah.
Okay. Other question? Yeah. 50? Okay, let's see. Oh, yeah. So we've got this revolving beam of light. So you've got a lighthouse, 500 meters off a straight shore, and the focus beam of its light revolves 4 times each minute. Okay. As shown in the figure, P is the point on the shore closest to the lighthouse. Okay. And Q is a point 200 meters from P. Okay. What is the speed of the beam along the shore when it strikes the point Q? Okay. Okay. So you've got like the lighthouse out here, right? And it's shining a beam to the shore. And directly across, we call this point P. Down the shore a bit, we call this point Q. And I guess I could do this. And I'm going to call that angle in between P and Q. Let's call that theta. Okay, what's this distance? That's
500.
They tell us, right? That's
Yeah.
500. And they also tell us the distance between P and Q is at 200.
That's 200, but also the beam of light is stopping before Q in the picture. I'm not sure if that's important or not.
What's that?
Beam of light is stopping before it hits Q in the picture.
Oh, yeah. I don't think that matters.
Okay.
I think it's just showing that it's swinging around. So this beam of light just kind of goes around and around, right? So at some point, though, it hits P and then it swings towards Q. Okay, which forms an angle. Okay, so what is the variable that maybe matters? Well, 200 is nice, but that's actually not needed right now. What I need to say is like between this line and wherever it is, there's some, wherever the beam is after P on the shore, there's some distance. So I'm just going to call that distance X. Now, when it's hitting Q, X is 200. But X could be 0, X could be 10, X could be 100, X could be all sorts of things. When it gets to Q, it's 200. So now I have this 500, this X, and this theta. This is a right triangle. How could I relate all of those? What equation would get theta, 500, and X all involved? Tangent of theta, yes. So I could say that the tangent of theta is equal to the opposite side, which is X, over the adjacent side, which is 500. Okay, so now I could take the derivative of both sides of this equation using implicit differentiation with variable time. I guess the interesting question here is, well, what is it that I'm actually trying to find here? That's always a good question to ask when you're doing these problems. It's like, what am I trying to find? So it says, what is the speed of the beam along the shore when it strikes Q? So I'm trying to find how fast, if I was measuring that beam of light hitting the shore, how fast is that beam moving? So what am I trying to find? dx dt. So if I'm trying to find dx dt, well, if I take the derivative of this thing, I'm going to get a dx dt, and I'm also going to get a d theta dt. Do I know what d theta dt is? I do, but I'm going to have to be a little bit careful. So d theta dt is going to be how fast does theta change over time? And it tells me in the problem that it revolves 4 times a minute. So that means in a minute, theta, what is theta per minute? So how many, it goes around 4 times. What's the angle of 4 rotations? 8 pi. So it rotates through 8 pi per minute, correct? So it's 8 pi per minute. Okay, is this, so what I'm saying is I want to know how many radians per minute, right? So if I'm trying to find d theta dt, I'm saying what's the change in theta over the change in time? Well, if time is 1 minute, then what is the theta? I said 8 pi if it's 1 minute. So that means that d theta dt is 8 pi.
Can you also take derivative of tangent theta, right?
Yes.
So tangent theta d theta dt.
Okay, so this is what it would be. So let's remember that d theta dt is 8 pi. Theta dt is 8 pi. But the derivative of tangent of theta is secant squared theta times the derivative of theta. And on the other side, the 1 over 500 is just a constant. It just hangs out. And the derivative of x is dx dt. So now to figure this out, I need to know what's theta or what's secant theta, whatever is more helpful. I need to know d theta dt, which I do. I need to know dx dt. Well, that's what I'm trying to figure out. So I really just need to know what's secant of theta. What is secant of theta in general? Secant theta is, let's see, it's 1 over cosine theta. Cosine is the adjacent over the hypotenuse. So secant is the hypotenuse over the adjacent. What is the adjacent side of this triangle? 500. So 500 goes on the bottom. Hypotenuse is this side. Well, what would that be? Well, I know that this side's 200. I know this side's 500. Could I figure out this side? Yeah, just use the Pythagorean theorem.
Could you also just use tangent theta and find theta that way? And that would still be the same theta, right? So you have 200 over 500.
Yes.
And then you just plug that theta into secant squared theta.
Okay, yeah, what is that theta? All that I'm saying is like, so tangent of theta is 200 over 500 or 2/5, right? So theta is tan inverse of 2/5.
Yeah.
This is starting to get like annoying to me, like plugging in tan inverse of something. That's not a nice number. It will keep numbers more nice, if you like, if you use this and then just plug in for secant of theta instead of trying to plug in for theta. Doing that is fine.
Yeah.
To be fair, there's nothing wrong with figuring out what theta is and just plugging it in and then taking secant of that and squaring it. But I think you're going to like your life more if you find secant of theta and plug that in. Okay. Yeah.
Can you also take the inverse tangent of x over 500 and then just derive from inverse tangent?
Yes. So that would be the other way to go, is that instead of starting with this formula, you start with theta equals tan inverse of x over 500. Then the derivative of theta is just d theta dt, and you don't get any secant at all. But then you get some more interesting things over on the other side, right? Which is fine.
Okay.
So yes, if you don't want to deal with the secant, you could just take tan inverse of both sides, and that's fine. Okay, seems like a good place to stop for today. So you can see that all of these problems, it's very interesting because they're all different, right? Because they all use different formulas and things, but in a way, they're all the same, in that every time you have to figure out what's the important formula, take its derivative, and then plug in the things you know. So obviously, the most important step of this is figuring out what's the important formula. And I think that something that we do wrong sometimes as mathematics students is we think that the important part of the problem is solving it. And it's like, well, that's true when you're like in pre-algebra or something, that like we need to learn to solve things. But the reality is that most of the time when you're problem solving, the most important part of the problem is figuring out what's the problem. And that is certainly true here. And it will be when we do some more story problems later, and this is actually just true in life. And that is that if you don't know what problem you're solving, you almost never solve it, right? And so the most important part of this process is figuring out what is the problem I'm solving. So you should be spending, there was this great Albert Einstein quote, and he said that if he had an hour to save the world, he would spend 59 minutes on figuring out what was the problem and 1 minute on solving it. And this is a good rule of thumb for mathematics students as well. It's like when you get a difficult problem, the majority of your time should be on figuring out what's the problem. And then you solve it once you figure out what the problem is. Often students that are newer to like kind of more difficult problem solving take the alternate approach. It's like they just throw together some formula that hasn't been well thought out and then start taking its derivative, and the original formula was wrong. So they're wrong. But it's like, so make sure that you get that first step right. And then you're almost, the derivation and stuff, like derivatives aren't that hard. The hard part is getting the right formula. So remember that as you're doing these problems, like spend the majority of your time figuring out what's the right thing to be taking the derivative of. And then the derivative part, that's not that hard. Okay? Have a good day. Have a good weekend, actually.